let's start with the lecture first, and then after we finish, I'll say something about the exam. Are you able to see your grades? I'm just kind of curious because I know you should be able to see everything after
I can see my
Friday.
grade.
I was able to see my grade.
So you can see your grade, but you cannot see your answers yet.
Let me just check. I'm not
And
sure if I can see my answers.
Yeah, me
yeah,
neither.
so after Friday, you should be able to also see the questions and everything.
Yeah, I can't see my answers or anything. Just
Yeah,
my
I
grade.
can see my answers.
So we'll say something about the exam after lecture, but let's
Professor,
get to the lecture first.
I'm dying.
Professor, is attendance
Yes.
during the actual live class mandatory, or would it be all right? Like, do you count attendance for each class, or would it
I
be
mean,
all right?
you can watch this later if you want.
Okay, thank you, Professor. Sorry, I have a thing I have to do.
So we'll do the lecture first. Hopefully, we'll finish it a little bit earlier if possible, and then we can say something about the exam. Now, the topic for today is we're going to talk about how to calculate, um, how to compute volume of parallelograms. Now, I put the word volume in quotation marks because we will develop techniques that will enable us to compute volume in arbitrary number of dimensions. So when the dimension is equal to 1, it's technically, so we say length. When the dimension is equal to 2, we say area. Okay, so when the dimension is equal to 3, we say volume. And so when d is equal to 4, we still say volume. So we'll just keep on using the word volume over and over and over again. And that's the reason why I'm putting it in quotation marks, because it's going to depend on what dimension you're located in. There's not really a name for when you're in 4 dimensions. What's the name of the measurement of the size of space that a body takes up? You just say volume. So we'll keep on using the word volume, but we should understand that it's volume relative to a certain dimension. So to avoid confusion, the way we're going to do this is I'm going to put an index. So we're going to just write this V subscript n. You're going to think of that as volume relative to a dimension. So if we were to write, for example, so if we write, for instance, so if the notation says V subscript 1, that is referring to length. It's referring to this. If it says V subscript 2, then it's referring to area. If it says V subscript 3, it's referring to volume the way you usually think about it. If it says V subscript 4, you cannot even visualize what's happening here anymore, but mathematically, you can still develop the rules so you can work with V4, and in general, we'll have rules to how to work with Vn. So it's a common thing that we do in math. We use the same symbol, but we index it depending on the different dimension you're located in. So that's volume. Now, when we say parallelogram, what are we referring to? So let's say what we mean by a parallelogram. So you see, the reason why we're going to be taught, well, let me say this. The reason we restrict our discussion parallelograms is because they are made out of straight lines. Straight lines. So it is an easier problem to solve. Later we will see how to compute volume for more general bodies. It makes sense that you sort of keep the problem a lot simpler. And after all, when we talk about linear algebra, it's related to the word line. So it only makes sense that we'll be talking about straight lines, and that's why we're going to confine ourselves to parallelograms. So, for example, in two dimensions, a parallelogram looks like this. So we know what that would be. You have something that looks like this. Okay, that's a parallelogram. In 3 dimensions, the picture is a little bit more complicated, but it's sort of the same idea. It goes something like that. And you can describe a parallelogram by using 2 vectors. So in 2 dimensions, you only need 2 vectors. So you would need, if you use this vector over here, and you use this vector over here, then these 2 vectors, they completely describe the parallelogram. So you can treat this, you can just treat that as your origin, for instance. And then if you use the sum of 2 vectors, that corner over here would be the sum of the 2 vectors. So if you just take the vector sum between these 2, that would immediately add up to the other corner. So these 2 vectors, they end up determining for you a parallelogram region that you're going to be calculating the area of. Now, in 3 dimensions, the way you do it is you need 3 vectors to describe a parallelogram. So again, if you think of this as your origin, for instance, you're going to have 3 vectors, and you only need 3 vectors to describe this solid. So this is now a solid. Here, this is a region, but this over here is a solid. And you can see that if you take these 2 vectors and you add them together, they will give you that corner. If you take these 2 vectors and you add them together, they will give you the other corner. And if you add all 3 vectors together, then all 3 of them will add up and they will give you the remaining corner. So you can get all of these corners of the parallelograms by just adding these vectors in different ways. And that's why you only need 3 vectors to describe a parallelogram solid. This is a solid, and you only need 3 vectors to do that. And the question is, how do you calculate the volume of such a figure? If I tell you what these 3 vectors are, how would you go about calculating the volume of the shape that is determined by that figure? So that's really what the discussion is about today. So let's introduce some notation, and we'll start writing down the properties. And in the end, we'll have the important rules to how to calculate these kinds of volumes. So here is the notation. So suppose we are working in n dimensions. So everything we say here, the rules will work in an arbitrary number of dimensions, but the pictures will be drawn in 2 dimensions and 3 dimensions. 1 dimension, that's a little bit too simple to really see what's going on. So most of the pictures will be in 2 and 3 dimensions, but the mathematical rules will work in an arbitrary number of dimensions. So suppose we're working in n dimensions, and we have a total of n vectors. So you have n dimensions and you have n vectors. So let's call these vectors, let me make this a little bit bolder. Let's call these vectors x1, x2, xn. And these are vectors, they're elements of this space. We're in n-dimensional space, and we have n vectors. So we have n dimensions and we have n vectors. So we use the notation, so this is the notation that we're going to use. We're going to write V for volume, subscript n, that stands for n-dimensional volume. And then we're going to put down the vectors that we have. So it's V1, so it's Vn of x1, x2, up to xn. And this is going to be equal to, by definition, this is the way we're going to define that quantity. By definition, this is going to be equal to, this is technically going to be called the oriented volume. The oriented n-dimensional volume of the solid of the parallelogram formed by these n vectors. So when we say the word oriented, so this word oriented means volume. That means volume is calculated up to a plus or minus sign, which is a little bit strange. Usually when you talk about volume, you're always talking about a positive number. But here, it will be helpful to work with oriented volume instead. So the reason why we will consider oriented volume as opposed to volume is because, as we will see, the mathematical properties for oriented volume are nicer to state. It's a common theme in mathematics that if you want to introduce a concept, it's often better to introduce it as an oriented concept. Like, for example, when you talk about the integral of a function, it's really, you say it's the area under the curve. Technically, it's the oriented area under the curve. You know that when you integrate backwards, you get a negative answer. If you integrate below the curve, you get a negative answer. So it's a lot of concepts in math, they just work better when you have it as an oriented concept. That means it's a certain measurement, but it's up to a plus or minus sign. So it's the same thing that's going to be over here, that it's not just volume, it would be volume up to a plus or minus sign depending on the orientation of the vectors. So let's just draw some pictures before we state some properties. So let's draw some pictures. Let's draw some pictures in 2 dimensions. So this is the way it's going to look like in 2 dimensions. Let's say you have 2 vectors. You have some vector over here, x. You have a vector over here. Call that x. And then we have another vector. In this case, let's call it y. And let's say we want to, now these 2 vectors, they end up determining for us a parallelogram. See, there's a parallelogram that is determined by those 2 vectors. And that parallelogram has an area to it. Now, the way we determine the orientation, it's, so here when you write, so if we were to write v2 of x comma y, in this case, this would be the positive area, because you can get from x to y with your right hand. So as we talked about the right hand rule, imagine that you put your right hand. So let me try drawing a picture of your right hand. So here's your right hand. So if you put the edge, if you put the very edge of your right hand, like this one down here, if you put it on the first vector, which is so this is your first vector. This is your first vector, that's your second vector. If you align the edge of your hand with the first vector, you can then curl your fingers towards the second vector and you can reach the vector. And your thumb is pointing straight up. Your thumb is pointing in the positive direction. That's the whole point. Your thumb is pointing positively. It is pointing up. It's pointing in the positive direction. So you can reach y starting from x in the positive direction. Now, if you do this backwards, if instead you write, if you reverse it, if you, for instance, if you would do v2 y comma x, then you would get the negative area. So you're still calculating the area, but the orientation here will play a role and you get the negative number. Because now imagine what's happening. If you put your right hand on the vector y and you try to reach the vector x by curling your fingers, you're not able to reach it. It's too far away. So what you have to do is you then have to position your hand to be pointing downwards. Let me see if I can draw it here. It's a little bit tricky to draw, but if you were to do it, if your fingers are pointing down like this, like that. Again, you have to line up your edge. So that's your right hand. So imagine that's your right hand. If you line up the edge of your right hand with the first vector, in this case, the first vector is y. That's your first vector. This is the second vector. So if you line up the edge of your hand with the first vector, and then you curl your fingers towards x, then you can see now you can reach the vector, but now your thumb is pointing straight down. It's pointing in a negative direction. So because of that, we say that the area comes out to be a negative number. Okay, that's what's happening here. So that's the way you determine the orientation. You determine it using your right hand. And the same kind of picture also works when you're in 3 dimensions. So let me draw a picture for you in 3 dimensions, and we see what we get. So let's suppose we have 3 vectors here. Let's make these up. So we have a vector. This is going to be x. Let's make up another vector. This is going to be, let's say vector y is pointing like this. And then let's suppose vector z, we have another vector. Let's make it bold so it stands out. And vector z, let me try that again. And vector z is pointing like that. So that's going to be vector z. And so you have 3, so you imagine that these are 3 vectors in 3-dimensional space. So it would be helpful for for visual effect to maybe draw some lines over here to make it a little bit easier to see. The solid, we have to draw the parallelogram solid. So here's your parallelogram solid that is being formed. Maybe this is somewhat makes sense. But that's your parallelogram solid that your 3 vectors determine. So that's your solid. So when you calculate the oriented volume, so in this case, V3. So we're in 3 dimensions. That's why we write V3. And let's suppose we do it in the order where x goes first, y goes second, and z goes third. Let's see if we can figure out. So this is going to be equal to the volume. So this is going to be the volume. And then here we're going to have either a plus or minus sign. It's the volume determined by that solid. But it's going to be determined up to a plus or minus sign. So we have to determine what's the correct sign to use here. So the way this is set up is this. So this is your first vector, this is your second vector, and this is your third vector. So we start with the first vector, x. We have to align our. So this is the way you have to align your hand. So just like before, it's going to be pointing like this. So the edge of your right hand, this is your right hand. The edge of your right hand has to be aligned with x. So they're aligned together. And now if your thumb is pointing down, your thumb is, you see your thumb is pointing down, you can now reach the second vector. So you're traveling from x to y using your right hand. So you can travel from x to y in this kind of a way, but when you do it, your thumb is pointing straight down, but the vector z, if you look at this vector z, it's pointing like that. So your thumb is pointing in the opposite direction of this vector z. So in this case, we have to use the negative sign. That's how we would determine the orientation. If that's not clear, maybe what I'll do is I'll put some pictures, some three-dimensional pictures on the problem set where I give you lots and lots of these to practice with, where I give you just a bunch of pictures and you try to figure out whether or not the orientation is positive or negative. And then when we have our problem classes, we'll just go over them again. For the purposes of this class, it's not super important to understand this because we will have mathematical rules for doing this. Like, the good thing is that we will not actually need to use our right hand to figure out the orientations in these problems because we're going to have the math rules are automatically going to do it for us. The reason why I'm talking about this is so that we at least understand how it's being calculated in a visual kind of a way so that the rules start to make sense. So when we write down the rules, so you at least understand where the rules are coming from. But when you're doing a specific calculation, the mathematical rules themselves will automatically determine for you the correct orientation. Okay, so let's start by discussing various rules of this. Maybe, so maybe this is like a helpful, so it is helpful to think of Vn. You want to think of Vn. It's kind of like a function in a way. It's a pretty complicated function. So you can think of Vn, this is the oriented volume, and this is called so it's called the n-dimensional oriented volume form. It's called a volume form. And the form, it's kind of like a function, but it's like a function. You see, you have n inputs over here, but it's a little bit complicated because you know that when we write a linear function, like when we write a linear function f, there's only like one input. Like we're putting in a single input, but the input we're putting into our linear function is a vector. This is like a function, but it's a lot more complicated because we're not just putting in a single vector, we're putting in n vectors, and every vector consists of n numbers. So that's, if you really think about it, that's quite complicated. It consists of n squared numbers. You're putting in, so again, each one of these is going to be an n-dimensional vector, but every n-dimensional vector has n numbers in it. So it's like you have like n squared numbers in total that make this up. So that's why we call it a form, because it's sort of like a function. It's just a little more complicated because there's a lot more inputs, but that's the way you want to think of it. So you want to think of it as a function. So it's helpful to think of this as a function where you feed a total of n vectors. Like you're feeding here, each of these, your inputs are vectors themselves. When you have a linear function, it's true, you could say the linear function is a function of n variables, but the variables are all real numbers. Here, you would say it's a function of n variables, but the variables here are all vectors. So it's that's why we call it, so the technical name, it's called a form. But anyway, that's what it is. So let's start, so let's let us begin by writing down some properties of Vn, of the volume form. And we will see why it is helpful to work with oriented volume instead. That's what we're going to notice here, that it's better to work with oriented volume. It just mathematically it works out better. So the first property, called, maybe we call it the scalar multiple rule. And by the title of it, here's what it says. If you're calculating the oriented n-dimensional volume of n vectors, so you have a total of n vectors, and then you have a vector somewhere, it makes no difference which coordinate. Let's suppose it's in position I, and it's being multiplied by some scalar, so you have a scalar multiple in front of it, call it A. So this scalar multiple rule, as you can guess, it's kind of similar to a linear function. It says that you can factor this constant out. So it will tell you that this constant, the scalar, can be taken out, and then you're left with whatever you're left with. So you have Vn, and then you write the vectors in the order in which they appear. So you have x1, you have x2, you have your xi now alone by itself without the constant multiple, and then all the way up to xn. So the reason why this works, if you draw pictures, it should be clear why this works. So let me draw a picture for you. Let us draw a picture to illustrate this. It will be helpful to use a two-dimensional picture. But the same idea works for a three-dimensional picture. So let's suppose you have two vectors. Let's call this one x. It's your vector x. And then you have another vector over here. Let's call it y. This is your vector y. And when you calculate the oriented volume, you're calculating the volume. You're going to be calculating the volume of that. That's going to be your volume. And that's what happens when you do V2 of x comma y. That's your oriented volume. So in this case, this is going to be a positive area, because here the picture orientation is that this is going to be positive. Now, let's say we multiply x by a certain factor. Let's suppose the factor is 3, let's suppose. So we now have 3x. We multiply it by a factor of 3. What is going to happen to our picture? Well, what happens with the picture is you are replacing this vector x by a multiple of itself. So the picture is that this vector will become 3 times as long. And so your picture would now look like this. The actual direction of the vector remains exactly what it was before, but now it is 3 times as long as it was before, and the vector y stays exactly as it was before. So y will stay exactly as it was before. And now you can see from the picture that if you calculate the oriented volume and you put in your parallelogram, well, it's exactly, I mean, you can see that it's 3 times as big. And you can see that now you have 3 of these. You have 3 of these parallelograms repeated a total of 3 times. So by putting in a constant over here, if you put in a factor of 3, what kind of effect does it have to the area? The effect on the area is now the area of this new picture, of this new parallelogram, will be 3 times as big as the area that was before. So it will be 3 V2 of x comma y. So that's what's going to happen if you did it. So you can factor that out. Now the nice thing about this, so the nice thing about using oriented volume is that this also works even if A, your scalar multiple, is a negative number. That's why we're using oriented volume, because mathematically this works. You see, if you used volume in the absolute sense, that you're only working with positive volume, you would have a problem with this. You cannot, if this number is negative, you're saying the volume is equal to a negative number. So you would have to fix it by maybe putting an absolute value of A. But then the problem is, anytime you start introducing absolute values into a mathematical expression, you're making the mathematical expression more complicated. It looks a lot simpler when you're doing it with orientation, because now you can just factor it out by itself without anything at all. And let's see why it works if you use a negative number. So now if you use a negative number, if instead of using x, you use negative 3x, what's going to happen is this vector is now going to look in the opposite direction. And so your picture is going to look like this. Your x, instead of pointing that way, it now points, it's 3 times as long, and it's now pointing in the opposite direction. This is going to be negative 3x. The vector y will still look the same as it was before. But now you can see from this diagram, when you end up calculating the volume, what do we get? Well, we get the exact same volume as it was before. Geometrically, it's still the same parallelogram. It's still the same exact volume, but the orientation becomes flipped, because if you use your right-hand rule, so V2, so if we do it like this, V2, so if you do V2 of negative 3x comma y, so this would be equal to, so if we say this in words, this is the negative area of the parallelogram. So that's why you're going to get negative, right? So it's going to be negative, but what's the area of the parallelogram? It is 3 times as big as the area that it had before. That was the area that it had before. And so you're getting that it's negative 3 V2x comma y. You can see that everything works out. So even if you're using negative numbers, even a scalar multiple is a negative number, it still works out precisely because you've defined everything using orientation. And that's the advantage of talking about oriented volume as opposed to just ordinary volume. So this is the scalar multiple rule. Now the other rule that is related to this, so this is the first property. The second property, I'm going to clear this away. The second property is, well, I should say where we're going with this. The goal of today's class is to tell you what the properties are. Once you know what the properties are, you can then use them to calculate various, you can use it to calculate certain answers. And then you do not have to rederive the properties again. Now, I could, of course, just tell you the rules and you just use them, but it would make more sense to tell you where these rules are coming from so you understand what these rules are and why they are the way that they are. So then you can use them and it makes sense for why they're being used that particular way. Of course, when you do calculations, you sort of forget about it. That's how often a lot of math works, that once you have the rules, you can often forget where the rules come from and just use them. But for understanding purposes, it's important to understand where they are coming from in the first place. So today's class, we're kind of just developing the rules. And then once we have the rules available, by the time we come back on Tuesday next time, you get to see the kinds of calculations you can then use it to get answers to various problems without rederiving the rules again. But it would make sense to derive them first. So this is the second property. The second property of Vn, of oriented volume, is called this one is called the alternating property. Alternating property. So it says this. So it says, so in plain language, it says if you switch the order of 2 vectors, the oriented volume changes by a negative sign. That's what it means in plain language. But mathematically, the way you would write it is like this. So if you have n vectors, and then somewhere you have a vector which we're going to call xi, and somewhere else you're going to have a vector called xj, and then you have xn. If you were to flip them, so if you were to take xi and xj, and you were to interchange those two vectors in the volume form, then you would get that it's the negative of what it was before. So it'll be negative of x1. So everything else stays the same, but it's just those two vectors are being flipped. So now this one is in position, this one is xj, this one is xi, and everything else stays the same. So you've done the flip, and you want to, the important thing here is you have to realize that you now have that minus sign. You now have this minus sign that comes up. So it says that if you have two vectors in your volume form and you flip them, you flip the orientation. A flip in the order of the vectors corresponds to a flip in the orientation of the volume. Now, you can see why this is true by drawing some pictures. So let's actually draw some two-dimensional and three-dimensional pictures so you can get to see why it works. So let's draw a two-dimensional picture. If you have two vectors over here, let's say this is x and this is y, you can see that in order to get from x to y, you have to travel in a counterclockwise way. But if you have y first, so if you have v2 x comma y, in this picture, this will be a positive number. It will be the positive, it would be the positive area of the parallelogram, because you can travel from vector x to vector y in a counterclockwise way. But if you do it the other way around, if you try to travel from y to x, if you flip them, you can see that now to travel from y to x, you have to travel in a clockwise way. And so you're changing the orientation, and now you're going to get a negative answer. So that's the way it will look in 2 dimensions. In 3 dimensions, it's almost the same picture. It's just a little bit more complicated. In 3 dimensions, the way this would look like is like, let's just draw it like this. So let's say that this is x, this is y, this is z. So these 3 vectors. So now if you try to calculate v3 x, y, z, you would get the positive volume, because, well, let's draw the picture here. The parallelogram would look like this. So that would be your parallelogram. And you can see from the orientation, so x goes first, y goes second. So if you start at x and you travel to y, you're traveling to y in a counterclockwise way, and then you can see your thumb is pointing up. Your thumb is pointing in the direction of z. So everything works out. But let's suppose you take x and y and you were to flip them. So let's suppose you change the order. Let's suppose you do instead y comma x comma z. You were to flip the order of x and y. You were to take these 2 vectors and you were to flip them together. If you were to interchange those 2 vectors, then you get a negative number. Now you can see why this works, because look what happens. If you try to travel from y to x, your thumb is now going to be pointing down. If you're using your right hand, the only way you can now get from y to x is if your thumb is pointing down, but the vector z is pointing up. So your thumb and the z vector are pointing in opposite directions. So by flipping 2 vectors, you flip the orientation. So this is what the alternating property says. And there's a nice consequence of the alternating property that we should mention. So let me get rid of these. I'll keep the property on the board, but I'll get rid of the pictures. So the nice fact of the alternating property is this. So as a consequence of the alternating property, if you have a repetition in the volume form, then it must automatically be equal to 0. So any repetition will make it be equal to 0. So what are we saying about this? Now you can see this both algebraically and geometrically at the same time. So for instance, let's say you want to find V3 of x, y, x, like this. So you have a repetition. That's what we mean by a repetition. There's a repetition in the volume. There's a repetition. The x is being repeated. So algebraically, look what happens if you take these two vectors and you interchange them. So if you interchange those two vectors, this is equal to negative V3. But if you interchange the two vectors, you get the same thing that you had before. Nothing changes. So you're getting that this number is equal to the negative of itself. And the only number that is the negative of itself is the number 0. That's the only number that could be. So if you have a repetition somewhere in the volume form, the immediate conclusion is that it must automatically vanish. The volume form must be 0. In other words, there is no volume. But geometrically, it also makes sense. Geometrically, it should make sense because since a vector is repeated, you are no longer forming a three-dimensional parallelogram. Your parallelogram is flat. It's flat. It has no volume. I mean, if you were to repeat your vectors, let's say this is vector x again, this is your vector x, and this is your vector y over here. So usually when you form a parallelogram, you need to have a vector sort of going out of those two. But what if your vector z is the same vector over here? Well, what if this is also your third vector? This is your vector z. Well, if you draw your parallelogram, then technically you have something which is flat. What's the volume here? I mean, the volume here would be 0. Because if you're working in 3 dimensions, this has no volume. It has an area, but it does not have a volume to it. So the 3-dimensional volume would be 0. So geometrically, it makes sense that if you repeat something, you're not actually creating the entire solid in your space that you want, and so that's why the volume comes out to be equal to 0. So this is our second property. And now let's mention property number 3. This is the third property.
Guys, can you go down for a second? Just for a second, so I can look.
Yes, let me
Thank
bring
you.
it down. So now let's mention property number 3.
All right, thank you. Got it.
So the third property is called the distributive property. So basically it says you can distribute across sums, right? I mean, we know, like, the distributive property for numbers says what? If you have a multiplied by a sum, that's just ab plus ac. That's what we call the distributive property. You know what the distributive property is. Maybe you do not know the name of it, because knowing the name of it is not important to do in a math problem, but that's what it is by the name. So you all know the distributive property. Maybe you do not know what it's called, but that's called the distributive property. And Vn has the exact same property. So let's write it down what it says. It says that if you have Vn and you have a bunch of vectors, so you have x1, comma x2, comma, somewhere you have an xi, and then you go ahead and you add to it some vector, let's call that vector y. We just add another vector to the ith coordinate, and then everything else stays the same. So we're just adding, you see, all we're doing is we are adding y to the ith position. Everything else is unchanged. Then the distributive property would say that you can distribute the volume form throughout just like multiplication. So in a very similar way, it would be x1, x2, xi, like that, xn, and then you would have plus Vn, x1, x2, up to, and now you just put in the y. That's the way you do it. And then you have xn, like that. So that's the distributive property. It says that if you have n vectors and you have another vector which you're calling y, and you decide to go ahead and add y to the ith coordinate, it makes no difference where you want to add it. You can add it on the first one or in the last one, but as you add it to the ith coordinate, then everything sort of distributes through, that these get paired. You see what it's saying? It's sort of like all of these get paired together, that you get them right over here, and then all of these get paired with y, and then you have the other one. So it's not exactly like the distributive, but it feels very similar to it. That's what it is. It feels very similar, that now you're kind of putting these together. And again, so here's the nice thing. This is the nice advantage of working with oriented volume. There is no such nice property for ordinary volume. Oriented volume just works better. It's a very nice property that you can distribute it through. Now, let me make a comment about this. This distributive property is tricky to prove. So what I'll do is maybe I'll make some comments on the homework to give you an idea how to prove it. So maybe a simple case of it will be posted on the homework for you to prove. The reason why it's tricky, if you try drawing pictures, it's not obvious at all. Even if you have two-dimensional picture, it's not going to be obvious. So if you calculate v2 of x comma y, like so. So here's the way the picture looks like. So here's x, here's y, okay? And now let's suppose you have v2 of x, y, and let's suppose we add to it a vector z. Then the distributive property would say, this is the question, why is this true? It's supposed to be equal to v2 of x comma y plus v2 of x comma z. That's the distributive rule right here. So it's almost as if you're multiplying in the x on each piece. You see, that's the distributive property. But if you draw pictures, it's completely non-obvious. Let's say, let's suppose your z vector is over here. That's your z vector. So now if you look at the picture, you have to look at the vector. You'll have to look at the area that is determined, the parallelogram that is determined by x and y. So this is the parallelogram that's determined by x and y. You have this parallelogram over here. And now you need the parallelogram that is determined by x and z. So this is the parallelogram that is determined by x and z. And you're somehow saying that if you take these two parallelograms and you add them together, that would be the same thing as if you were to replace y by y plus z. Now, if you do the rule of addition involving, maybe I have to zoom in here so you can actually see this a little bit better. So you have to do y plus z. So y plus z. When you do y plus z, you end up actually somewhere over there. Okay, and you're saying that the parallelogram that is like you're basically saying, I mean, so here's like the pictures that you're getting. I know it's very complicated because they sort of start colliding with each other, but these are the three parallelograms. You have the blue one, you have the red one, and then you have this outline of the third one. And you're saying the blue one and the red one together have to combine, and they have to give you this outline of what would happen if you added y and z together. That is completely not obvious why it has to work like that. It's not clear from the pictures themselves. It's not clear from the pictures themselves why it has to why it works like this. So on the homework, I will give you some idea about how to make this work, but that's basically the distributive property that it says that you can distribute it in on each of the pieces. The one case where this is easy to see the special case where it's easy to see geometrically why this is true. The one special case where it is easy to see why this distributive rule works is if the vector y is chosen to be one of the other vectors. So if this y over here is chosen to be one of the other vectors, so like for example, let's say you put it over here in xj, some other vector, then it's easy to see. I mean, if you draw a picture of that, that's going to be easy to see. And I'll put it on the homework for you to justify why it works in this special case. And then from this special case, you can then argue the more general case, why it then works for an arbitrary vector. So some work is definitely required to justify this distributive rule, this distributive property. But that's basically what it says, that if you have a sum in the volume form, you just distribute it through and you add them up, and then you keep on going from there. And let me mention the very last property, and this very last property is actually the easiest property of all. And then we can start, and then we can do our very first example of how you use all of these properties to find the volume. So let's mention this is the very last property. The final property is called, I'm not sure what to call it. Let's call it the unit cube property. It says that if you take the volume form of the standard basis vectors So that was a mistake. These are the standard basis vectors. These are the standard basis vectors. You get, anyone see what you get? What you get if you do that? You can draw some pictures. So these are the standard basis vectors. You can try drawing some pictures in 2 dimensions and 3 dimensions to see what you're getting. So like, for instance, if you do it in 2 dimensions, you're working with 2 basis vectors, the 2 standard basis vectors, E1 and E2. And then in V3, you have E1, E2, E3. Can you see geometrically what you're supposed to get?
Do you get n? Or no, you get n cubes?
So you get n cubed. You get this? Anyone getting a different answer? So this is E1. This is E2. And you want to find the volume of this. In this case, the area of that. Here's the picture in 3 dimensions. These are like the ijk vectors. This is E1. This is E2. Well, technically, E1 is the vector that's pointing towards us. That's the vector on the x-axis. This is the vector on the y-axis. This is
Would
the
it
vector
be
on the.
v to the n power?
So you get v to the n power. So this v. So you're saying this v. What does this v represent?
I guess I would say like the volume, because you're multiplying out the vectors out together.
Right, you are multiplying the vectors together to get something, but in the end, what's the volume that you're supposed to get? Like if you look at this picture, what's the volume of? Well, in this case, what's the area of this?
It'll be like E2 times E1.
So, what's like the final number you're getting?
With the area, isn't it 1 of E1, E2?
Right, it's just 1.
Yeah.
This is 1 and this is 1. These are unit vectors. These are the standard basis unit vectors. Now, what volume do we get over here?
There's also 1.
Right, it's also going to be 1. So when you said v to the n, maybe what you wanted to say is you wanted the v. You probably wanted to say that's the length of each side, and the length of each side is 1, right? So that would be 1 to the n. So this would it's like 1 to the n. So in the end, in the end, it's just 1. That's why it's called the unit cube property, because when you use the basis vectors, you're creating a cube, which is the simplest type of parallelogram. This is the square. We just call it a cube. In general, we just call it a cube because we allow ourselves an arbitrary number of dimensions. So this is a 2-dimensional cube, otherwise known as a square. That's a 3-dimensional cube, otherwise known as just a cube, like in ordinary language, that's a cube. Its volume is 1. And when you have n basis vectors, you have an n-dimensional cube whose volume is 1. So if you write the standard basis vectors in the order in which they are written, you get 1. Now, if you were to start to interchange these, you're going to start changing the sign of that because of the alternating property. So we have enough time to do one example, one very simple example, and then we'll say something about the exam. So these are the 4 properties. And the nice thing is that using these 4 properties, and without drawing any geometry, any pictures at all, you can easily calculate the n-dimensional volume of any parallelogram. So for example, okay, so here's a simple example. Let's do a 2-dimensional example. So we have a parallelogram. So one of our vertices, so these are parallelograms at the origin. If they're not at the origin, you can just slide them so they're at the origin. That's not a big deal. So let's suppose this corner is at 1, 1. This corner is, well, let's make it 2, 1. Let's say this one is going to be at 1, 5. And then, so the other one, the remaining one, has to be the sum of these two. If you want to form a parallelogram, you have to take the vector sum of those 2 vectors. So the vector sum of the remaining ones will be at 3, 6. So by doing that, you end up creating a parallelogram. That's your parallelogram. Okay, I know that the sides are not actually parallel because it was just not drawn in the best possible way. But this is x, This is y. So this is going to be x. This is going to be y. Okay? And the volume of the parallelogram, let's say you want to find v. So in this case, it's v2 because we're talking about area. So that's a two-dimensional measurement. How do you find v2 of x comma y? Well, you're going to use the standard basis vectors. This is going to be equal to v2. So you take x and you write x, which is the vector 2 comma 1, and y, which is the vector, in this case, 1 comma 5. You have to write it in terms of the standard basis vectors. So this is v2. If you write this one in terms of the standard basis vectors, this is 2e1 plus 1e2. And now if you write this one in terms of the standard basis vector, this is going to be 1e1 plus 5e2. Okay, and you're going to notice this is quite elegant how everything works out. So now what you do is you can use the distributive rule. Use the distributive rule, sort of distribute it in on each piece. So you would get v2 of 2e1 plus e2 comma e1, and then plus v2 of 2e1 plus e2, and then multiply. I say the word multiplied because it's similar to that. It's not technically multiplied. 5e2. Okay, what do we do next? You distribute again. Now you distribute the other way. You can kind of distribute this on each piece. Just distribute that in. So you use the distributive property again. So this will be v2 of 2e1 comma e1, and then plus v2 of e2 comma e1, plus v2 of 2e1 comma 5e2, and then plus v2 of e2 comma 5e2. Like that. That's what happens when, now you could, of course, if you wanted to, you could have done like, it's basically just like multiplication in a way. I mean, you can just imagine that you're multiplying things out. I mean, look at this. It's almost as if you're doing this multiplied by that, which gives you this, which gives you all of that. And then you can also do this. I mean, it's basically like multiplying out two terms in a way. But I wanted to do it very carefully just to show you how the distributive rule is being used. Now, here's the nice fact. Remember the alternating property and the repetition property. You have E1 and you have E1. Because these two vectors are repeating, well, let me do this first. This 2 can be factored out, right? This 2 can be factored out. But after you factor out the 2, you're left with E1 and E1. And that's a repetition. Where you have repetition, you have zeros. This is 0. And this is 0. Those have to be zeros because you have repetition in the vectors. That's the repetition property. If you have repetition in the vectors, when you calculate the volume form, it comes out to be 0. Now let's see what we're left with. This is the unit cube property. You see, you're left with the unit cube, E2 and E1, but it's written in backwards order. So you put it in the correct order, where they're written in the correct order of the standard basis. So this will be minus V2 E1 comma E2. That's the way you write it. That's the correct order you have to use here. And then you have plus, you have 2 and 5. These are constants. You can factor out the 2 and you can factor out the 5. Here you're using the scalar multiple rule for 2 and 5. Together, when you factor them out, that will give you 10. So you would have 10. And then you have V2, and you're left with E1 comma E2 written in the correct order. So now everything's written in the correct order. And now you use the unit cube property. This is a two-dimensional cube, in other words, a square. And this is a square. And the orientation here is correct. It's written in the correct orientation. So this one is equal to 1, and that one is equal to 1. So we're able to replace this. We're able to say that this is 1, and we're able to replace this and say it's equal to 1. So in the end, we get -1 plus 10. We get -1 plus 10, which is equal to 9. It's equal to 9. So the final answer to our problem is 9. The area of the parallelogram, in a very elegant way, comes out to be 9. You see that you do not actually have to find the height and the base and the angle or any of that. By just using these rules, it automatically tells you that the answer is equal to 9. And you can do this in an arbitrary number of dimensions. You can do this with a 3-dimensional solid. And these rules extend for any number of dimensions as well. You do not even have to visualize it anymore. Now, that's just one example. And we'll have more examples when we meet on Tuesday and we continue to discuss this further. But that's the way it works. These are the properties. Like, knowing the properties alone allows you to do the calculations. Now, let's say something about the exam. I do not think you can see, I think your grade, yes, like I said, your grades should be visible after Friday. So after Friday passes, you should be able to see your grades.
I can see my grade right now.
Okay, I meant to say, yes, you should be able to see your grade right now. I meant to say you should be able to see which questions you got right and which questions you got wrong. That's what I meant to say. You should be able to see it after Friday to see what kind of grades that you got correct. Now, here's what you do. So let me just mention some important stuff, some important detail. The exam grade, the maximum possible score, not including extra credit, is 80 out of 100. The remaining plus 20 points will be given in person on exam 2. Okay, so exam 2 will start off with 2 manual by hand calculation problems. For exam 1. And then followed by the new topics. That's the way it's going to be formed. Because I did make a promise for you that for exam 1, I wanted to give you 2 manual problems to do by hand, like classical type of problems where you just have to calculate things out. In fact, I'll tell you what the problems are. The 2 problems will be, I'll tell you what they are. I mean, you probably already know how to do that. You're going to have to invert a 3 by 3 matrix, okay? And then, as a follow-up, do matrix multiplication to show your answer, to check your answer. Because, you know, when you get the inverse, the product with the matrix has to be the identity. So you'll do 2 things. You first find the 3 by 3 inverse by hand without using a calculator. And then you multiply your answer with the matrix to check if your answer is correct. And if you can do those 2 things, which I imagine almost everyone in this class can do, because that's the much more straightforward part, you would just add an additional 20 points on the exam. So let's suppose you get, so let's say on this exam it says you have 70. And that includes the extra credit. Let's suppose you did 1 extra credit problem, you did the mandatory problems, but you only got 6 of them correct. So you include the extra credit, you now have 70, and then you can be confident that assuming you can do this, which I think is by far simpler than any other question on the exam, because the other questions on the exam, if you saw, even though they were not computational, they were more conceptual. If you can do that, assuming you can do that well, and this basically comes down to understanding row reduction, you can just add that to it. So if you're getting like, so if you check your grade and it says 70, that's 70, whereas the maximum possible score was an 80. There's still 20 more points available to be added to that. Okay, and it's the same thing. If you got a 60, if you get this correct, your grade's going to be an 80 for exam 1. Now, after you find your, after you can see which answers are right and wrong, you can start checking your work for partial credit. And then you'll let me know. So, this would be an acceptable, so let me give you an example of it. This is an acceptable exam dispute. You can say something like this. I solved, let's say, problem 4 correctly, but I forgot to divide out by this number, and here is my, okay, and then you can say, and you can check my screenshot. And then I'll look at your screenshot and you get full points. Okay, this is full points. Okay, that would be full points. You can also say something like this. I started solving problem 4 correctly. I did this and this, which is required, right? That's just you would say that's a required step, but I did not know how to proceed beyond that. And that could be, I mean, it depends on what the work did. It could be half credit. Maybe it would be like 6 out of 10 points or 7 out of 10 points, depending how much work went into it. That would be fine. So this is, now this is what I would call a confusing exam dispute, would be something like, can you check all of my work? It usually indicates, like in my experience, usually when people say something like that, it's because they did not get the problem correct and they're not able to find any kind of partial credit, and then they want to see if there's a way for them to get extra points. This is confusing because then I'm not sure what I'm checking, and there's a lot of emails to go through, not just this class but other classes. So that would be very difficult to figure out something like this. So it would be better if you can tell me what I'm looking for and what I need to be looking for so I could make the adjustments. Now, also I should say there is plenty of time to get this all fixed until exam 2. So please be patient, and we will eventually get to you. There are, as I indicated, there's also questions that students have coming in from other classes. So if you send an exam dispute for me to look at, it might take some time, several days, until I get back to you. It does not mean that you're being ignored. It just means that I'm doing it like one step at a time. There is no rush here. The important thing, I mean, the most important thing here is that you have submitted your work. You have submitted your work. That is your evidence. We have your evidence. The fact that we have your evidence means we do not have to rush this. We can do this very patiently. We can go through one problem at a time until you find something. And just take your time to look at the way you are doing the problems, go over it, and let me know if there are adjustments that need to be made. Now, the good news is a lot of people did very well. The good news is about 40% of the class got 80 or above on this exam. As I indicated, 80 is kind of like the maximum in a way, because there's still a follow-up question worth another 20. So a lot of people did very well on this exam. So for most of you, that should not be an issue. If you go above 100, that goes for extra credit. That's what it would mean. So that's all what that means. So if you have 110 on this exam, then the additional 10 points, when it gets calculated in the grade, it just goes over, and it's just becomes extra credit at that point. Anyone have any questions about some general exam stuff? So the good news is people did very well in this exam. Usually, oh, and this is kind of funny, by the way, if you're wondering, I'm not surprised why people did very well in this exam, because almost every single person in this exam, in this class, is a computer science student. You would be surprised, but some of the weakest students you have in a math class are math students. You say, how can that be? The reason is because the math program, it starts off generally very easy. I mean, Calculus 1 is very easy compared to everything else. And then Calculus 2 is a little bit harder. So the math program progressively becomes harder and harder and harder. And then people get to advanced calculus, which is substantially harder than anything they've ever seen before. But the engineering program, I think the computer science program, it starts off really hard in your first year. I think the engineering programs, they typically become a little bit easier towards the end of your degree, because you're doing projects at that point. It's not so much exams. All of the difficult exams were done in like your very first year, whereas the math program is kind of backwards. So a lot of the students in the math program, they might have dropped out of the engineering program and they said, I'm going to do math because I passed Calculus 1 with a C. And now you have all of these people in the math program. And in my experience, whenever I teach a class that has, like, it's a linear algebra class that has a lot of math majors in it, it's like, I would say maybe like 60% of the class or more ends up failing the exam. And so anytime you have if you have a math major in your class, it means one of two things. Either that student's going to be at the top of your class or at the bottom of the class. I mean, that's often the way it goes. There's not many that in between. But in my experience, whenever I have like engineering students or computer science students, it's always a great exam performance. So this is a great exam performance, and hopefully this will continue until the end of the semester, and then everyone will get some really good grades at the end of this course. And you will find it helpful for linear algebra, because many of you who are in computer science are probably at some point going to be doing, maybe some of you are interested in machine learning and things like that, and there you have to use a lot of linear algebra. So that's something that you will find helpful. So if you do well in this class, it'll probably help you later on in your path in computer science. So everyone have a good day. Wait until Friday night. Yes, go ahead with your question.
Yeah, my question. Can you hear me?
Yes.
Yeah, my question is, what's the like the title of the topic that we discussed today? If I wanna search on Google, to learn more.
It is written on the syllabus. So if you go on the syllabus, there's like a schedule day by day for what we're doing.
Okay, got you. All right,
and then you can find it there. What I'm doing is a little bit unique. It's not usually discussed in books, but I'm doing it because it will help clarify the topics.
So